We're privileged with two speakers sharing our platform today and sharing the speaking time. They are Johane, Nienkemper, Swanepoel from the University of Stellenbosch in the Department of Statistics and Actuarial Science. She has a diverse history, starting out in at the University of Stellenbosch, at the University of the Free State, where she did a bachelor's and master's degree in statistics, and then moved to the Department of Genetics, if the records here are correct, at the University of Stellenbosch, then completed her PhD at Stellenbosch and moved into the Department of Statistics and Actuarial Science there. So that she has an interesting background. And the other speaker, second speaker, is Zoe-Mae Adams, who started out, if our biography center is correct, in economics and Bachelor of Economic Science, and then migrated to statistics. The original degree was at Stellenbosch, and I think she is, if my records are correct, she's still at the University of Stellenbosch, and she works in multivariate text visualization, multidimensional text visualization, and she was supervised by Johane. They will be speaking today on multiple correspondence analysis, biplot applications, missing data, and text analysis. Over to the speakers.
Today we're going to show you some background on multiple correspondence analysis, specifically biplots of multiple correspondence analysis, which we in short form call MCA. And first I'm going to show you just basic background on MCA and biplots, and then my application will be aimed at missing data problems, and Zoe will then continue with text analysis problems. But all of the visualizations that you'll see today are MCA biplots. So these are the two of us, which you now know more about us. So we are also based in the Center for Multidimensional Data Visualization, where we have a lot of active research projects that we are working on. Towards the end of the presentation, Zoe will tell you about our flagship project and where you can learn more about that. So yes, I am fortunate to be able to supervise Zoe, and lucky for me, she is also interested in the field of biplots, and specifically the MCA biplots we'll be looking at today. So yeah, it just shows you that you can always find something overlapping between researchers where you can work on something together, and we hope that you can see our passion today here on the work that we are continuing with. So just a basic summary of the type of data that we'll be considering today: multivariate categorical data. So typically, as you might know, data is summarized in a matrix with rows and columns, and we refer to the rows, mostly we refer to it as samples, but some people also refer to it as the observations, and the columns refer to our variables, which can also be referred to as characteristics, because you're measuring characteristics of your observations. So for our context, the possible measurements will be finite qualities, or what we call categories. They can be unordered, then we refer to nominal scale data, or they can be ordered, which is then ordinal scaled data. I think Zoe will also mention a bit more about this, but the assumption we make in this MCA biplot that you'll be seeing today is that we work with nominal scaled data, meaning that there's no specific order of importance between the categories of our measurements. Of course, there are cases where you can look at the ordinal scale, but this will be the focus of today. Also, for categorical responses, your observations can have what we call response patterns, unique response patterns, which summarizes the combination of the responses of these category levels, which are the values available for the variables. So typically you would recode your multivariate categorical data matrix in the form of an indicator matrix. And an indicator matrix consists of a dummy coding, so it will be zeros and ones, which would reflect the specific response of a category level. So as a basis, if you have two categorical variables, you can typically summarize those frequencies of occurrence in a cross tabulation, which we call a contingency table. And now, if you have a contingency table structure data, you can apply correspondence analysis, CA, which is a dimension reduction technique, which at its core is based on singular value decomposition, which I'll tell you a bit more in a few slides. But the aim is that you want to obtain a visual representation, so a lower dimensional representation of a multidimensional data set. So of course, I've been telling you about the multivariate categorical data sets, so correspondence analysis will not be sufficient for that. And that's why we use multiple correspondence analysis, which is an extension of this correspondence analysis technique, but now you can express your multidimensional data in a lower dimensional representation for several categorical variables. Now, there are various approaches to apply MCA. We're only going to focus on one specific approach, and that is to apply correspondence analysis on this indicator matrix that I've briefly mentioned. So to give you an idea of the data structure and what an indicator matrix is, I've taken this example from the UB-Bibble 40R package. UB stands for Understanding Biplots, as you can see there, and this is a textbook from 2011, if I'm not mistaken, and the authors of that book, Professor Leroux and Professor Libbe from Stellenbosch University, have this R package. So this is just a small example of a multivariate categorical data set where we have our 7 observations, so 7 samples, and then we have our 1, 2, 3, 4, 5 categorical variables. And as you can see here, they have various response levels. So for the biological sex, we have 2 levels. For hair, we have 4 levels, and so on. So when I say levels, I mean the categorical responses that are available per categorical variable. So then to recode this data matrix into an indicator matrix, it would look like this we see in this bottom table of the matrix G. So for each category level in this matrix X, we now have a column. And if the response level corresponds to that column name, you will indicate that with a 1, otherwise a 0. Now, these zeros and ones are important in the methodology of MCA. If you would take the sum per column, we could call that a column weight. So for instance, for the biological sex female, we can see the sum here is 3, and we have a sum of 4 for male. So the sums per column will become a column weight, and then the row weights will always be the number of variables in your data set. If you sum these ones per row, you will see you get the number of variables, in this case 5. So that's just how the indicator matrix is set up. Yeah, I've just isolated hair color specifically to make it slightly easier to see. So we can see here for the variable hair, we have 4 category levels, and this is the representation of this variable in the indicator matrix. So the singular value decomposition, it is a powerful dimension reduction technique, and I want to say very popular and frequently used. And it enables a lower rank approximation of a high dimensional data set, as I've mentioned. So not to go into too much detail, we are now aware of what the matrix X is. It's our categorical data matrix with samples and columns represented in the rows of the variables and the samples represented in the rows and the columns. And we know now we have an idea of the total number of category levels. So this matrix R and C you see here, it's just weighting our indicator matrix with regard to the row weights and the column weights that I've mentioned on the previous slide. So we reweight this indicator matrix and then obtain the singular value decomposition solution of that reweighted indicator matrix. And that's then what our solution will be based on. So I'm sure the slides will be available so you can go through this at your own time, but I've just defined some of these reweighting matrices for those who are interested. So that's just the background on multivariate categorical data and the approach that we follow to recode it. Now I just want to jump in and give you some background on biplots before I show you my applications. So starting with the continuous data, biplots are for the visualization of multivariate data, so meaning more than 2 variables. The prefix bi stands for mode, so it doesn't refer to 2 dimensions, as could be the assumption. It means that we are going to simultaneously visualize 2 modes or 2 entities, which in this case is the sample information and the variable information. So it's typically referred to as a generalized scatter plot, where a scatter plot summarizes 2 continuous variables, and you have your x and your y axis. But for the multivariate case, we have to then extend this so that we'll have more than 2 axes. There would be an axis per variable. The number of samples or the observations will still be the plotted points, which shows the association of the 2 variables in this visualization. The positioning of the axes refers to the correlation between variables, and then the proximity, so how close the points in this display lies, how close they are to each other, that would relate to the association between these samples. So some of the benefits of scatter plots, not scatter plots, biplots, I've summarized here just by means of 3 principles. And I just want to give a shout out to Dr. Karel van der Merwe, which he agreed that I could use his lovely summary here. So basically this slide just shows us what we can use or gain from using biplots. So firstly, the scatter plot is easy to understand, especially we all are familiar with the 2-dimensional scatter plot. It allows us to be able to interpolate new occurrences into this display. We can have calibrated measurements if we project a particular point perpendicularly to these axes. So this is something that I think we're all very familiar with. Then it has this added benefit of dimension reduction, so that we can have more than 2 variables and summarize it still in 2 dimensions, but visually we can then look at the relationship between more than 2 variables. So in this display, maybe it's a bit small, but these red lines represent the new axes, so an axis per variable. And then the points you see here would then refer to our sample points as in a typical display. And then it affords us the opportunity to obtain calibrated axes per variable. This is not shown in this biplot here in the center, but one of the main benefits of our biplots are that we can calibrate these multiple axes and then project each of these observations to the various variable axes and obtain approximated observation values in 2 dimensions. So just quickly going to run through this small examples. So here we can have our typical scatter plot. So you'll see here this data table on the right. I'll expand it systematically. So we have 2 variables represented on the X and the Y axis, and then we have the 3 observations with their corresponding values for variable 1 and 2. So we can change the origin of that display. We haven't changed anything about the information, but we can move the axes around. We can then still project the values and nothing has changed. We are still displaying the same information. We can also rotate this. This will not affect anything about the interpretation. And then we can also change. So we have tilted the axes slightly, but we are still able to project the points perpendicularly to an axis and read off the values. So that's just to show you by moving the origin, adding a rotation, we still have a standard scatter plot, but this then makes it easier to kind of see the progression to a biplot where we can then add a variable. So yeah, I've added a 3rd variable, and we can see that we can still project each point perpendicularly to an axis to read off the values. So I'm not going to go into detail here, but you can of course see that there would be some variability in the projections, because we are reducing the higher dimensional problem to 2 dimensions. So there would be some a prediction error, but the goal is to, of course, get the biplot which approximates your optimal solution the best. And here I've just added a 4th variable. but I think we are more or less comfortable about what a continuous biplot could be. And I just want to kind of build the steps to where we are heading for the categorical cases. So typically, to construct a biplot, we use our singular value decomposition that I showed you with the explanation of the indicator matrix. But we can distinguish between two types of coordinates, and we call them the principal coordinates and the standard coordinates. And the difference between these two are the contribution of the singular values. So what's contained in that diagonal matrix of sigma, and I said I don't want to go into too much detail, but the point is that there is a contribution of the eigenvalues that differs for the two types of modes that we want to summarize. So in order for the distances in the biplot that we observe to be meaningful and that we can interpret them, the coordinates have to be in this different scale. So the one has to be principal coordinates and the one has to be standard coordinates. So typically we would plot the first two columns of this U sigma, which is the principal coordinates, and that will represent the samples. And then for the column representation, we would plot the first two columns of V. Now, if it's a continuous biplot, as I've shown, you will have calibrated axes. But for a categorical biplot, you'll have two types of coordinates. One will be the sample coordinates, and the other will be the category level points. That's what we call them, the CLPs. So they represent coordinates of the columns in the indicator matrix. So there are various scaling parameters that can be used to obtain different looking biplots, but this is the base of how to construct a biplot. So for our categorical data, as I said, the two types of coordinates, they will be represented as I show here, with the sample coordinates being the addition of our eigenvalues, which is not present in the category level points. So here in the categorical biplot, the distances between the coordinates show us again association, and we can interpret the distances between these coordinates as they are plotted asymmetrically, meaning the one is principal and the other is standard. So this is the same example that I showed at the beginning when we explained the indicator matrix. I just want to see how I'm doing on time. So the squares are now representing the samples and the triangles are representing each level of the categorical variable that we showed. So I've just highlighted a few of the observations to kind of get a feel of how to interpret this. So if we look at observation George, these are the category levels that are assigned to George's response profile. And if this was in the full dimensional space, the closest category level point to George would be the response that was selected. But of course, since we are reducing the dimension, there is some variability. So sometimes the closest category level point would not always be the one that is in the response profile. But typically that is how we would interpret that. So that is Jane and her category levels that were assigned in her response profile. And then I've also just indicated a few more. So to see associations between samples, what I've done here is just give us some ellipses of George and Harriet. And we can see that they have overlapping responses. So because George and Harriet are in close proximity to each other, we can make the assumption that they have similar response profiles. And as we can see, all of their responses overlap apart from the biological sex. So that's just in a nutshell how you could interpret the categorical biplot. So for missing data, just some background on that. It's assumed that data goes missing due to a random process called the missing data mechanism. There are three defined mechanisms. Missing at random means that your missing observations have some dependency on the observed information. Missing completely at random, that's just a simple random sample. So the missingness does not depend on the observed or the missing information. And then missing not at random is when your missing values depend on the other unobserved information. So these are the three known mechanisms. And it's important to know what the mechanism is because you can't just apply the same missing data technique for all mechanisms. So that's why it's an important first step in your analysis process to understand why is it missing and can you possibly identify the cause of missingness. So as I've explained that the missing at random and the missing completely at random have a different way of a dependency structure towards the observed information. And we thought that it could be then an interesting avenue to see whether the proximities in this biplot, MCA biplot, could maybe tell us something about the dependency as well, because as I've said, the proximity of points show us the strength in association. So from that, we started this is a first article on that with subset multiple correspondence analysis. So subset meaning that I'm going to be able to show the missingness and the observed information separately by recoding the indicator matrix in a slightly different way as before. So what I have here is a missing simulated data set, a very small case, 3 variables with various category level points. They can take on 3 different values, 1, 2, and 3. And then we see we have some missing values in here. Now, a standard indicator matrix will result in these blocks of zeros that you see here. But if we apply an additional recoding, which is called the single active handling, we create a new category level per variable, which is the missing category level, and we assign ones where there is missing value. So again, the same dummy variable allocation. If it is a particular level, a 1 is allocated in that position, otherwise a 0. Now, what this then does is we can get back to the row margin or the row weight that I've explained by adding this new category level that is specifically assigned for a missing value. Now, by doing this, we will be able to subset information that is observed and then also look at a subset of information that is missing, which is then the subset multiple correspondence analysis approach. Now, I don't want to go into any detail of what this data set was, but again, it's a simulated example to show you on the left, it's the complete data set. That's what the biplot of that particular example would look like. And on the right, it is a missing data problem of the same data set, but applying MCA. Now, we don't have a lot of time, but I think we can, everyone see that these open circles are more dispersed in the missing data biplot, so the SMCA biplot. But we can see that the same structure, meaning where the location of the points are, is more or less similar from the left to the right. So this just shows us that we went too far. This just shows us that it is possible to recode a multivariate categorical data set and then display a biplot even though we had missing values at the start. Now, you can really go and read that paper, but what we found is that this SMCA technique is only suitable for higher percentages, is not suitable if you have high percentages of missing values. It truly is only suitable when you have low percentages of missing values, meaning less than 10%. But as I showed you here, it does preserve the overall structure, which is reassuring. But the true benefit is actually showcasing the visualization of the missing subset. So what I showed you here was the visualization of the observed subset. So the idea was here to utilize the idea of proximities. As I said, the missingness mechanisms have a dependency structure which we can utilize. So the argument was then the closer variables are together, this could maybe translate to a dependency. And if we see that missingness in one variable depends on another, that could maybe be linked to a missing at random mechanism. So I'm going to skip this slide just to kind of save time. So what we did is we used a clustering technique, a clustering around medoids, which is the PAM method in R. We have references at the end of the slideshow. And in this package, you have a silhouette coefficient, which tells you how separable your clusters are in a visualization. So this value can go from -1 to 1. And the assumption is that if it's well separated, meaning you can see different structures, so that's a 2-minute warning for me. You can see more than 2 different structures. So they can be separated. The silhouette coefficient will be more than 0.5. And if it's not well separated, meaning you can't really see any dependency, it's all just muddled together, that would be a silhouette coefficient that's less than 0.5. So I'm going to rather show you, this is another simulation case what you are seeing here in the 3 left panels are missing at random mechanisms that were simulated. You'll see here that they are simulated with different percentages of missing values. Don't worry too much about these distributions that were simulated, rather just focus on the green patterns that you can see. So I think it's fairly clear that we can see towards the right, these green dots are all on top of each other. There's no particular structure. So I want to use the word it's random. Whereas with the other 3 to the left, the 3 columns and 3 rows to the left, we can clearly see that there's some kind of pattern resulting. So again, I'm just focusing on the samples, but there can be some underlying information and the variables as well, but just focusing on the green dots for now. So what this showed us is that there is some evidence that if you have a missing at random mechanism, which we've simulated, we can see that there is a sample structure, whereas if it's a missing completely at random simulated example, there's no structure in this MCA biplot of the missingness. So we went on and confirmed this even more. So I'm going to add in the chat a link to the Shiny application, and you can play with it yourself. So you can simulate your data, you can choose your variables, samples, which distribution you want to simulate from, and what's the percentage of missingness you want to simulate. And then you'll be able to visualize the complete SMCA subset biplot and the incomplete one on the right here. And the idea is that you want to go and see if you can see a specific structure in the samples. And then also in this program, a clustering is done. So the clustering will then give you the silhouette coefficient. And what we've found through simulation is your silhouette coefficient is more than 0.6. This is a strong indication of a missing at random mechanism. So this is just in a nutshell. I know it is very rushed towards the end, but in this Shiny application, you can go and upload your own categorical data, and you can try and identify the mechanism of missingness, which will then assist you in deciding which type of handling, so which type of missing data handling procedure you can then apply. So I have some application steps here for you, but the point is that you run SMCA, meaning you want to get a visualization of a missing data set. But first you have to recode it so that you can subset between missing and observed. And then, as I've said, if you have a high percentage of missing values, you would rather want to go for an imputation technique and not the specific technique. But the true gain here is to go and look at the subset of the missing data to get an idea of why your data is possibly missing. And then you can also try and confirm it with our clustering approach before you decide on a handling technique for your data. So I'm going to hand over to Zoe now. Let me stop sharing. And she will then continue on with the text applications.
Thank you, Johane, for the good start. Maybe now I don't even have to explain MCA biplot. Okay, so my section will focus on the application of how an MCA biplot can be used to visualize insights regarding text data. So this will be our final product, so it will get there in time. So just as a start, where text data comes from. So due to the advancing digital technology, a majority of our communication as people these days occur on digital platforms like social media. So it becomes easier for researchers to actually extract this kind of data so we can actually gain more insights about social patterns, societal trends. But that's more with regards to when it comes from subjective text data. So text data can either be objective, such as text data from these such as these examples on the screen with the scientific articles or scholarly journals. And you can also have more subjective text from blog posts or user-generated text from maybe Tumblr posts or poems. Those will be much easier to analyze if you want to see more about how people interact with each other. So my focus will be more on a social basis, and kind of detecting human behavior in some sense. So our focus, or this focus, will be on subjective text, although most of text analysis procedures or techniques are built from objective text data. This one will be focused on subjective text. So just the background on text analysis before we get to the actual visualization part of it. So we first need to create the type of data set that we will be working with. So just to start with, what do we do with the text data? So in its raw format, it's difficult for the computer to understand what exactly to do with it. Thus, we will use text analysis techniques. So text analysis is a very broad field of techniques, but we will focus on very few. One of the fields within text analysis, natural language processing, since the subjective text will, or user-generated text will refer more to natural language of how people interact with one another. So we will need processes that work with that. So it is according to the slide, it is a subfield of AI that focuses on the interaction between computers and humans through natural language. And it enables computers to understand, interpret, and generate human language in a way that is both meaningful and useful. So we are focused on understanding, or the techniques will use with understanding natural language, not necessarily generating. Generating the natural language is actually more with regards, if you think of a very sophisticated way of natural language generation is actually something like ChatGPT, which is not going to be the focus of today's analysis that I'll be showing the examples of. So in order for us to go from the raw text data that we have that you can actually extract using something like application programming interfaces, so the APIs, we will first need to mold the data into a format that we can actually work with. All the type of processes that are entailed within that is pre-processing. So this is the first thing that you do, where you can take your raw text data and clean it up so that you can actually use it for further analysis. It involves tasks such as noise removal, punctuation removal, or handling of punctuations, not always removing it, stop words, handling stop words, and other irrelevant elements. So the irrelevant elements will be dependent on the type of analysis that you are interested in. If some of these elements are relevant to your analysis, then you would keep them in. So that is still something that can be handled quite manually. But this is some of the examples of pre-processing. So in order to make sense of that, or just to go through our example, this will show most of these steps that have been mentioned in the pre-processing techniques. So where we have an example sentence that we can work with. So the example reads, the cinematography in this film is breathtaking, capturing the essence of the setting perfectly. So yeah, we have it's very subjective. So this could be referred to some kind of review of a movie. So the first step, or you can start with converting to lowercase. So in this case, in our example sentence, only the T will be converted to lowercase. In the second step, that's why I had it in the text in blue. Second step would be to remove punctuation, since the final product that we will, or the final format of the text observation that we'll work with won't necessarily need punctuation at all. So we can remove that. So the only punctuation we'll remove here in the pink is the comma and the full stop at the end. So that thus we are left with the sentence without uppercase letters and punctuations. Then the third step, which will be most useful for the analysis that we'll be working on, is tokenization. So this will split or divide our sentence into smaller elements or smaller things called tokens. So each word in this case will be considered a token. So yeah, we only have it only changes the format of the sentence. So we will basically left with a vector of text tokens that we can look at individually. So here we have 14 tokens from this one observation. So after we have tokenized it, we can look at all of the individual elements, and then we can start by removing stop words. For this analysis, stop words, we will end up working with the attitudes toward the cinematography in this case. So we don't really need the stop words for the further analysis. If the analysis does need stop words, then you can keep it in and skip that step completely. So the stop words in this case will be the words such as the, in, this, is, the, and of. So there are at least 3 those. Removing those, we'll be left with a vector now of 7 tokens instead of the 14 that we had. So this also, pre-processing can also be seen as a form of dimension reduction as well. And then one of the last steps you can do in this case is stemming or lemmatization. So if we look at the, oh, that was supposed to be capture. So the word capturing will be reduced back to its stem. So rather than, so capture can be captures, capturing. So this will just put it back into its stem word, capture. And then also perfectly will result in perfect. So that will be easier to compare to different lexicons, which we will also talk about a bit later. So our final observation or sample will be a vector of 7 tokens. So these are our observations, and thus we can use that for analysis. So before we go on with the example of how we will analyze this, let's go back to kind of try and link to the type of data representation that we've worked with the MCA biplot. So how will we go from this type of vector to the MCA biplot? So what we'll need for the MCA biplot is a multivariate categorical data set. So in order to use text data, or to go from text data to categorical data, is that we can use text classification to obtain categorical variables related to the text. So text classification, we will use assigning each text observation or text sample to a set of categories. And you can extract, either you can calculate some certain values or do different types of classification based on external information, or you can extract it from the text observation itself. So you can see that here are examples of quite a few things that you will be able to extract from text observation, such as a review or blog post by the without having to get external information. So word frequency, parts of speech tags, sentiments, which will be the important thing for us, and genre, language, and authorship. So for each observation, you will be obtaining a classification or categorical variable, which will have category levels that we can also use for the data set. So in the next slide, we have an example of what our data set will look, or categorical data set will look like. So each row will represent a sample or a text observation, such as in this case, individual tweets, or original tweets. This was based on a study from my master's, where we obtained tweets and extracted them with the keyword COVID, just so we can look at what people were saying about COVID-19. This was extracted in about 2021. So here we have 3 samples as an example. Here we have in the second or the third column, if we think about that one as a column, you have words considered for classification. So these are words that can be matched to sentiment lexicons, which we'll talk about in a while. But the main thing here is the 4 columns, and at the end, this will be considered our X matrix. So we have in observations or in samples, and in this case, we have 4 categorical variables. On the next slide, we can look at the category levels of these variables. So we have 4 categorical variables: location, number of words, sentiment classification according to one of the sentiment lexicons called the AFIN lexicon, and the Bing sentiment classification from the Bing sentiment lexicon. So sentiment lexicons refer to words, lists, or refers to 2 columns of data, or that existing words or phrases that have predetermined sentiment scores related to them. So you have one, we'll look at the example, we can see what they would look like. So that's what we mean, be matched by existing words with predetermined sentiments. So location, in this case, we'll only look, or the examples that we'll look at a bit later will only be referred to the cities or the cities of the countries. So here we have, for either case, we have 3 category levels. Number of words that could be classified by both lexicons. So these are nominal categories from 1 to 5. So there's 5 category levels. This will have an effect on the indicator matrix. So this, for that section of the indicator matrix, this will have 5 columns for the numwords variable, 3 columns for location, 5 columns for this sentiment classification, and 3 columns for this one. So we'll have quite a FD of an indicator matrix. The number of observations or samples were at least 334. So it's quite a large, well, not as the largest I've ever seen, but quite a large indicator matrix to work with. So this will be how we will go from the text data or text processing or text analysis to MCA biplot representation. So this is what our multivariate categorical data set will look like for the resulting plots that we'll see towards the end. But before we get to the MCA biplot, there are other text visualization techniques in order before we other than the MCA biplot. So we can have word clouds, bar graphs, tree maps, or heat maps. However, these maps are mostly focused on the frequency at which words occur. For example, vaccine and news were just the most frequently occurring words. So we can obtain a summary of what people thought in that large set of text observations. So we'll take a set of tokens. So if we can think about the entire data set of text observations into small tokens, these tokens will be used to obtain these word clouds, but based on how, the frequency at which they occur. So, but how will we get to the MCA? So for purposes of text visualization, in our case, we want to look at, similarly to with the MCA biplot, where we looked at similarity or associations among samples and category levels. This is also the whole aim of MDS, or multidimensional scaling. We can visualize similarity between observations in a reduced dimensional space. Thus, it will, when we have categorical data, this will lead us to the use of correspondence analysis. So this MDS is also a very broad field of different types of visualization techniques, but we will focus on correspondence analysis. This is a screenshot from the Kusher and Kieran paper, where we looked at a survey of all existing text visualization techniques. There are many techniques available. However, not the MCA biplot was our approach on a different type of visualization technique. So going back to text classification, we've mentioned some of the things about sentiment classification already, but sentiment classification is one of the forms of text classification, but the categories are related to sentiment or emotions or attitude. So identifying and extracting this emotional intent, we can actually go back to what we wanted to see from the subjective text, where you can find social patterns or mental health indicators, any kind of subjective information. So thus we'll move more towards a sentiment classification. So if we find observations being similar, we can also maybe see if they're similar in sentiment towards something. But the focus will be visualizing the sentiment classification result. So the methodology used for the sentiment classification, it's not the only one that exists. As we've just highlighted, we use the lexicon-based tidy text approach, since we're not trying to, the focus was not to find a new way to perform natural language processing or sentiment classification. We just want to visualize the results more effectively with the MCA biplot. So we mentioned before the comparison to the sentiment lexicons. We're matching text elements, so the tokens, to terms in the sentiment lexicons. The ones that we used for the examples were the Bing lexicon, which is the most popular one to use when it comes to sentiment lexicon based. Well, it's just a very trustworthy one. And then we have the AFIN lexicon, where we have scores ranging between -5, which indicates very negative, and +5, very positive. So Bing can either be negative or positive. So we only have a binary classification over there. And with the AFIN, either from, so there we have a much more categories, and it gives us more information on the nuance of how negative or how positive the sentiment is for that term. So just to see how it will work to match the sentiment lexicons, example sentence. So here we have, the game was exciting, we had a great time. So following the same steps with the previous, from previously with the text analysis example. So here we are also left with a vector of tokens. So also with a lowercase and removing punctuation. But here I highlighted the two words exciting and great, because these are the words that can be classified to either sentiment lexicon. So exciting and great. So within the Bing sentiment lexicon, this is just an excerpt of what the lexicons look like. So here we can match it to the word exciting from our observation to the one in the lexicon, to a positive sentiment, and the same with great and to positive. The AFIN lexicon, we have the scores ranging from -5 to 5, exciting as a score of 2, and great as a score of 3. So in order to create a categorical variable from that and from this matching, we can, for each observation, find one category level. So the Bing category determined by the majority classification. So if most of the words are classified positive, it will have a positive score. But with regard to that analysis, we also found that some of them can be neutral when they balance each other out. So that's for cases where we have one positive word and one negative word in the observation. This will result in a neutral score. And then AFIN scores are calculated as a weighted average. So since both of these words, that's actually supposed to be 3, were at a score of 3, or no, it was 2 and 3, and it had a weighted average of 3, this will result in us having a category of 3 to 5. So this was also created manually, where we could just rather have 5 categories instead of from -5 to +5. So this will be classified to that score. So this will bring us back to what the data set looked like. So here we have an example of what the AFIN classification looks like and the Bing classification looks like. So each observation will have a sentiment score and for both lexicons, location, and the other one was numwords. So this was the MCA biplot as a tool for sentiment visualization was something I didn't really come across. So this is just from a few of the survey articles that I found on sentiment visualization. Not a very thoroughly researched field yet, but we can represent sentiment analysis results in order to gain insights into the emotional tone, attitudes, or opinions expressed in text. We can create graphs, graphical representations to help understand and interpret patterns across different text categories or time periods. So here's just some examples from a paper also listed in the references by Kusher, Paradis, and Karen in 2018. So our approach to sentiment visualization, firstly, was this part of the first step was to look at organization text visualization, word clouds, and then adjusted for sentiment. So the green words are classified as positive and the red was negative. But we can just, so this was just the first approach, but we rather looked at the MCA biplot after that. So do look into word clouds. We can look at these plots, but I don't think we're running out of time. So back to finally at the MCA biplot. This is our standard MCA biplot. So very similar to what Johane mentioned, or the results Johane had. So this is how we can interpret this specific MCA biplot. So here we have the AFIN category for neutral and the Bing category for neutral. So as expected, we would expect these category levels to appear close together since they should have the similar sentiment because that's how they're classified. So this highlighted the consistency of the sentiment lexicons for correct classification. Same here, we have a negative sentiment category group and a positive sentiment category group. Here we can find the numwords category levels appearing not close together, but what we would assume is that words with two classifiable words are more associated with neutral sentiments, and words with many words are more associated with positive sentiments. Yeah, we also have the locations close together, so we didn't really see a lot of difference. So since they are appearing close together as a categorical variable, there isn't much difference in sentiment related to the location of where a tweet was posted from. So this interpretation allows us to gain insights on the category levels. But here we also have in the scatter plot, or the gray dots in the similar scatter, in the different other mode of the biplot, we want to find certain observations are associated with numwords 2, or with positive sentiment scores and with negative sentiment scores. Before we go on to the next plot, the shape. So Johane did mention about the scaling. So you can see that there's a certain shape occurring among the category levels that looks a bit like a horseshoe. So the horseshoe effect is one of the effects, known effects within multiple correspondence analysis, since it assumes that the scaling is nominal. However, when it comes to sentiment scores, such as these going from negative to positive, they shouldn't really have the assumption that they're nominal and should rather be considered ordinal. So this is a known effect or a known issue within MCA, but there are different coding approaches to deal with that. But for now, we're just going to stick to this. This will be covered in the next phase of my research. So this is already already very effective in interpreting this plot. So we can see the category levels, the consistency among the lexicons, but we can't really see which samples are associated with which categories. So that brings us to our embedded word MCA biplot, where we would embed the words classifiable from this data set, or from this example. So this will be the word considered for classification, as a text label for each observation. So here we can, for example, look at the AFIN or the negative sentiment group, and you can see that words associated with that sample point is fake, fake, worse, fake. So, and also with positive, there are positive words. So that was quite successful. However, this becomes very cluttered since a lot of the points have the same location or are overlapping on that one point. So thus, finally, we looked at the interactive embedded word MCA biplot, which will have the exact same interpretation. However, now we don't have to deal with the cluttering of this plot. I'll just play the video. So this will allow us to hover over the points in order to see which words are associated with which category levels. And we can also see that the category levels are still represented. On the left, you can toggle between, so there's the link that you can also follow when the slides are shared. We can, between cities or countries, so the two data sets that we used. You can also toggle between tweets, seeing the original text observations extracted, or just the words that have been considered classifiable. And then you can also toggle between the number of extracted words, so the numwords column from the data set. You can see that there's a lot of, very few, there are more words for the 1 and 2 group for numwords, but 4 and 5 have significantly less observations. But that could also be due to some other things. But the plot in this format, in the interactive plot, is much more useful, but the interpretation does remain the same, but we can also gain additional insights or interpret it much easier from this type of plot. So the interactivity is very useful. So this is our embedded word MCA biplot. So it is useful for text visualization because we can look at associations among samples, amongst text observations, amongst category levels, just to see if certain samples have similar sentiments. and can be used for many other things. So this is still a bit of this is definitely not the final interpretation of this, but there's a lot more to be done. But this was definitely found very successful with regards to how we can use an MCA biplot for text and sentiment visualization. Okay, so that is the plot, so that we can continue. So these are our references. Not the exhaustive list of references. We can also definitely provide more. The software, as Johane mentioned, these are some of the packages that we use for both of our analyses. And this is some marketing for our Movisu group. Please go look at it. It was very, very hard work, but also it should be very user-friendly. And we'll also welcome any feedback with regards to our package. So do go look at it. This is, as a user-friendly, it's supposed to be an easier use of biplots. Do go look at it. The vignettes are very useful with regards to theory as well. So you can also use it as some references. But yes, so that's just some marketing. We are very passionate about biplots. This is just scratches, our presentation just scratches the surface on how it can be used. So this is just our applications for missing data and text analysis, but there are many, many more. So yes, thank you so much. I hope the time's still fine. Thank you so much for listening to us. You can ask any questions if need be. Thank you.
Thank you, Zoe-Mae, and thank you, Johane. Are there questions from the audience? Okay, then how much of this is used behind scenes in Bing, analyzing your social texts and Google searches on comments and things like that?
Interestingly enough, I think Bing was a good base to use the sentiment lexicons, but I think more sophisticated models these days that use these kinds of sentiment, they don't necessarily go for the classic Bing lexicon, but they probably used something a bit more unsupervised, so that the machine, or so that it can learn as it goes along. So it's also a lot faster, because this is quite time consuming when it's a very manual process. I think theoretically Bing makes sense, but I do think that they did use Bing as a foundation, but built on that for sure. Yeah, so I think behind the scenes they've gone way past that, but it's still good to theoretically think about it. Yeah.
Thank you. Any other questions? There's a question from the audience here. You want to stand over there?
Hello.
Hello.
I would like to find out from Dr.
Zoe-Mae is
Yes.
bottom screen, and the middle one is Johane.
Hi.
Johane. Hi. I would like to find out from your missing data biplots, has it been applied in banking data?
Well, not by myself. I don't know how widely read the papers are, but maybe there are some applications I haven't seen, but you can definitely apply it to it. Are you working in that specific sector, or is that your interest?
Well, no, I'm a mathematician working a bit now, but I worked in corporate for 7 years.
Okay.
And we have encountered issues with data with missing information, and also data which we do not have any information about. And this in the past, it has always been we have always used statistical inference for the missing data. But I was just thinking that this might be a good way, other than
Yes.
the inference method,
To be able to do an exploratory analysis. So I must say the techniques I showed today was for the non-technical user, but it would be a much better approach to apply multiple imputation. I also have done research on that, where you can visualize also with the MCA biplots, but first doing a multiple imputation on the missing data, constructing biplots for that and then combining it into a final visualization, I would say that would be a better approach. But long answer short, yes, you can apply these techniques to any field, any type of data. The question is just with regard to the missingness, which would be the best approach. But lucky for you, there is also an expert in the room, Professor von Maltitz, on missing data. I see he's online. So if he would want to add something, but yeah, but you're welcome to send me an email as well if you want to chat further.
No, it was, it's just something which we encountered, and there's a lot of debate around that when I was working in corporate. And
I can imagine.
Yeah, there was a lot of sort of, I have more experience and I'm telling you, this is how we do it. Not very scientific, which made me very, very uncomfortable. And because everything you do, you have to be able to justify it scientifically.
Yes.
So yes, that was one of those things which I found that could be a possible research topic, but obviously I left that 9 years ago. So I don't know, maybe there's a new technology now and people are doing it or whatever.
Yeah, hopefully it's not just deletion.
Yes. Great,
But
thank
yeah.
you very much.
Thanks. We have copied the links of the Shiny apps in the chat. I did it a while back. I hope you can see both of them, but I see Zoe has also added it now. So yeah, it would be nice if you go and play around with that as well.
Thank you. And all of those links and the videos are available on the CoE website. So if you didn't catch those links now, you can always go to the CoE website and watch the videos and stop them at the relevant points and pick up the links. Is that correct?
Perfect.
And then thank you for joining us. Thank you for the interesting talk. One and combined. And it was very good to hear some new and interesting ideas. Thank you.
Thank you so much.
Yeah, thank you for providing us with a platform
Yes.
to talk about it.
Thank you.
All right.